This is lesson number 3 on forces for Year 7 Science, and I've called it Forces Acting on Objects. So in the first 2 lessons I introduced what forces were. A force is basically a push, pull or twist, and it involves interacting with an object. And forces come in 2 main types. You've got a direct force or an indirect force. Another word for direct force is contact force. That requires physical contact. And an indirect force or a non-contact force doesn't require physical contact. So an example of a contact force is friction. You rub your hands together when you're walking. There are 2 surfaces that you need to interact. So in the case of rubbing your hands, you need your hands, obviously. When you're walking on the ground, it's the bottom of your feet and the ground, the floor. Examples of non-contact forces include gravity, the force that keeps us on the ground, on Earth's surface, and magnetism. The things that you put in your fridge, they're magnets. They use magnetic forces. Today I want to look at, in this video, forces acting on objects. So if I have, let's say, a box resting on a table. Let me draw a table. Here's a box with a lid. And suppose the box is just sitting there and we want to study the forces. What do? Well, in science, scientists like myself, we're quite lazy. We don't like to draw things all day. We like to do things a lot simpler. So we go from here, from this diagram to this diagram. Now there's different ways to draw this. I just prefer using circles. So to represent the box, I'm going to be using a circle. Okay, this is the box with the lid. It's just quicker to draw. It's much quicker to examine, to look at. So looking at the forces on the box, I'm going to draw a circle like that. Now there are 2 forces acting on the box. There's a force that every single object on Earth has. It's called a weight force. And the way we draw a weight force, so we start from the middle of the box. That's where the weight force acts. In the middle of any object, including you. I'm going to use an arrow to represent the force. So forces, a force is represented by an arrow in science. Okay, because forces are things that have a size, a length in this case, and a direction indicated by the arrow. So looking at this box here, it's got a weight force that's acting downwards. Okay, when we weigh ourselves, obviously we need to stand on the scales to weigh ourselves. Okay, because there's a force pushing down. And obviously the heavier you are, the higher the reading is on the scale. So that's called the weight force. Different ways to write weight force for short. Sometimes, so in science, we like to do things quite simply. Capital W for weight force, okay? If you write capital W for Year 7 Science instead of writing weight force, that's acceptable in a diagram like this. But that's not enough there. There's also another force that acts directly opposite to the weight force, and that's called the normal force. Now my diagram will be much better than yours if you're going to be drawing this. It's called the normal force. Now why does this make sense? Well, if you think about it, if there was no normal force, gravity would literally be crushing us all the way down through to the Earth's center. And that doesn't happen every day, right? What happens is there's a force that opposes that weight force, and it acts directly in the opposite direction. It goes upwards. It's called the normal force, and it acts 90 degrees to the surface. In this case, the table. I'm not going to draw the table, but you can see, I'm sure you can picture the table as being there. It's at 90 degrees to the table. In other words, it's perpendicular. In maths, perpendicular means 90 degrees. So the normal force always acts perpendicular to the surface. And we usually write capital N, okay, N for normal force, okay, and the W is for weight force, W for weight. That here, that is called a free body diagram. Free body diagram, also called FBD for short. Free body diagram. Free body diagrams are great because what they do is it's a picture that shows an object and all the forces that are acting on it. Okay, and it's called a free body diagram because the object is free from its surroundings. We don't care about the table or anything else around it. We don't care about the people around it, or if there's a car parked outside. That's irrelevant. We don't need that stuff. We only care about the box. We're interested in this thing here. So that's why we call it a free body diagram. And so that's the free body diagram for a box sitting on a table. You have a weight force, it's got a weight. If you measure its weight, it could be, let's say, I don't know, 10 kilos, let's say. But the normal force will also have to be 10. Now, what I should be saying rather is the weight force, not the mass. So forces are measured in newtons. Forces measured in newtons, named after Isaac Newton, famous English scientist. Capital N for Newton, okay, in his honor. So obviously the higher the newtons, let's say an apple is like 10 newtons. Or let's say 1 newton, I should say. And let's say the box weighs 50 newtons, for example, a really heavy box. Okay, the box has a higher weight force than the apple, obviously, right? Because it weighs more. Same thing with a car versus an elephant. An elephant has a greater weight force than the car. So forces are measured in newtons. The more newtons, the more the force. Suppose I put the box now on an inclined surface, okay? An inclined surface, and it looks like that. It's just sitting there. Once again, the forces will look like this. So the weight force will go directly down, capital W. However, the normal force, because the surface is now inclined, it's at an angle, the normal force will have to look like that and not vertically straight, because that's your 90 degrees there. If you get a protractor, that's what your 90 degrees will look like. Okay, because the normal force is always perpendicular to the surface. The surface here, the box is sitting on, is at an angle. Okay, and that's 90 degrees there. So just a heads up with that. Let's look at another example. Let's look at a box sitting on the floor, and it's being pulled to the right by a rope. Someone's pulling it, okay, that way, by a rope, and here's the rope here. And we need to draw a free body diagram. So instead of drawing all this, which takes forever, free body diagram. So the box, we'll use a circle to represent the box. Now, what forces are there acting on the box, okay? So let's look at the Y direction. The Y means it's going up and down. Think of maths. Got the Y axis, the vertical axis. Well, we've got the weight force acting downwards always, and you also have the normal force acting straight up, okay, in the opposite direction. You have a tension force. Now, strings, ropes, and rubber bands, and slinkies, springs, they have a tension force. It's basically a force that they produce when you pull on these things. And it's acting to the right, okay, because it's pulling it to the right. Capital T, okay, tension. Capital T is for tension. Tension is a force produced by these things like ropes. Now, when you move something, when you're moving, in the opposite direction there's friction acting on whatever it is, in this case the box. So I'm going to draw an arrow to the left. A smaller arrow than the tension arrow. Whoops. Okay, because the size of the arrow indicates the size of the force. If the frictional force, so I'm going to call this capital F, okay, that's friction. Right, if I'm walking, let's say, to the right, friction will act towards the left. Okay, it's going to try and oppose my motion, slows me down. If friction F, that arrow on the left, is bigger than the arrow on the right, the tension force, well, I should say, sorry, if they're the same size, the box is not going to go anywhere because they'll cancel out. So the tension has to be bigger than the frictional force F. So let's draw this in a free body diagram once again. I've got the weight force, so from the center of the circle roughly, weight force acting downwards. So using a ruler and pencil here for these diagrams, I've got to mention, when you're drawing diagrams in science, always use a pencil and ruler. And you've got a normal force acting upwards. Let's say they're both 2 centimeters in length. And then you have the tension force acting to the right because it's being pulled to the right, capital T. And you have a friction force, slightly smaller arrow, acting to the left. And that's how you do free body diagrams.